Welcome to the Deep Dive. We're your shortcut to getting smart fast. Today, strap yourselves in, because we're tackling 3 centuries of scientific, well, let's call it creative chaos.
Yeah, creative chaos is a good word for it. We're not just talking small tweaks here. We're diving into a massive revolution in physics from the 1600s to the 1800s. Basically how scientists wrestled with light, electricity, magnetism, and, what's actually in the space between planets.
Right. And our mission today is to track this incredible, sometimes brutal struggle, how they built these grand theories only to see them, crumble with the next experiment. Is fascinating.
It really is. And you have to remember the context. The old certainties were gone. Copernicus, Galileo, they'd flipped the old view of the cosmos. The telescope was showing new stuff almost daily.
So they needed more than just a few new facts.
Exactly. They needed a whole new operating system for reality, a complete system of human knowledge, as they saw it.
And stepping up to the plate was René Descartes. Quite the ambition.
Oh, immense ambition. Descartes wanted to build this entire structure on reason, on mechanical principles. He saw the universe as this giant machine, everything just pushing and pulling, motion and pressure.
Which meant no empty space, right? Because if things like light or gravity had to travel, something had to be carrying them.
Precisely. No vacuum allowed in Descartes' universe. Space had to be a plenum, completely full.
Full of what, though?
Full of this invisible, all-pervading stuff he called the ether. For Descartes, everything light, magnetism, gravity, it all had to be explained by tiny ether particles swirling, bumping, pushing each other around. It was the only way mechanics could work across space.
Okay, so they have this mechanical framework. How did they start applying it to things they already sort of knew about, like static electricity or magnets?
Well, people knew about amber attracting things. The Greeks called it electron. And magnets, lodestones were ancient mysteries, too.
But then they started getting more systematic.
Yeah, like Peregrinus, looking at magnets. He noticed how they always lined up, like the Earth itself, and he was the one who said, let's call these active points poles. That's really the beginning of thinking about polarity.
And then William Gilbert, around 1600.
Right. Gilbert did a ton of experiments, showed it wasn't just amber, rubbing glass, sulfur, gems. Lots of things created this attraction. And he's the one who coined the term electric for this specific force.
Sticking with the mechanical idea, how did Gilbert explain it? No spooky action at a distance for him either, I guess.
Definitely not. He imagined that electrified things gave off this sort of atmosphere, an atmosphere of effluvia, tiny particles that physically reached out and grabbed things.
So his own kind of mini ether, basically, just for electricity.
Kinda, yeah. It's all about needing contact, even if it's invisible contact. And Descartes, of course, had his own detailed version for magnetism. He imagined these swirling vortexes of ether fluid going one pole of a magnet and out the other. Very mechanical.
Okay, so this mechanical thinking led to a pretty famous clash over light, didn't it? The law of refraction.
Oh, absolutely. A classic case. Descartes derived the math for how light bends when it enters, say, glass or water. He used an analogy like a ball hitting a surface.
Makes sense, mechanically.
It did, but his model implied something specific. Light had to travel faster in the denser stuff, like glass.
And then came Fermat.
Yes, Pierre de Fermat. He approached it completely differently. Not with mechanics, but with the principle. His principle of least time. Nature always takes the quickest path, he argued.
Okay, a philosophical idea?
Right. But here's the kicker. Using that principle, he derived the exact same mathematical formula for refraction as Descartes.
Wait, the same formula? But based on a totally different idea.
Exactly the same formula. But, and this is the crucial part, for Fermat's quickest path principle to work, light actually had to travel slower in the denser medium. Slower in glass, not faster.
Whoa. So you have the same correct math, but predicting opposite physical realities.
Precisely. Faster in glass or slower in glass. Both theories gave the right answer for the angle, but they painted completely opposite pictures of what light was doing. It really forced a choice. Trust the mechanical analogy, or trust the elegant mathematical principle.
Which brings us right into the big fight over light in the 17th century, particle versus wave, right?
Yep, the central battleground. On one side, you had the corpuscular theory, most famously championed by Isaac Newton. Light is made of tiny particles shot out from the source.
Like little bullets.
Kind of. But even Newton noticed something wave-like. He saw that white light could be split into colors, and he described homogeneous light of a single color as being periodic in its nature. Different periods, different colors. That was a huge insight, even if he stuck with particles overall.
And the other camp.
That was Christian Huygens pushing the wave theory. Light is a vibration, a disturbance traveling through that all-pervasive ether we talked about.
Makes sense, like ripples in a pond.
Exactly. But Huygens ran into a problem. He looked at two beams of light crossing each other, and they didn't seem to crash or interfere, they just passed right through. So he concluded maybe interference just doesn't happen with light.
Which held back the wave theory for a while.
For about a century, yeah. Newton's authority was huge, especially in England, so the particle view mostly won out. Until the early 1800s and Thomas Young.
Ah, Young's double-slit experiment. Well, not quite the double slit yet, but his work on interference.
Right. Young showed definitively that light does interfere. If you make light arrive at a point via two slightly different paths, sometimes the light adds up and gets brighter, and sometimes it cancels out and gets darker. That's classic wave behavior.
And he had that killer argument with Newton's rings, too, didn't he?
Yes. Newton had studied these colored rings you see when you press a lens against a flat piece of glass. The very center spot, where the air gap is thinnest, practically zero. It's always black.
Which is weird if light is just particles bouncing off, right? Shouldn't it be bright?
Exactly. If it's particles, why darkness? Young explained it using waves. He realized, drawing an analogy with sound waves hitting different materials, that when light reflects off a denser medium like the bottom piece of glass, the wave gets flipped. It's retarded by half a wavelength. Its phase shifts.
Okay.
So the wave bouncing off the top surface meets the phase-shifted wave bouncing off the bottom surface. When the gap is zero, they're perfectly out of sync and cancel each other out completely. Black spot. It was proof positive of wave behavior, and it confirmed Fermat's idea. Light must slow down in denser media for this phase shift to happen.
Okay, so waves are looking good, but there was still a big puzzle, wasn't there? What kind of wave?
Right. If light is a wave, why doesn't it bend around corners easily like sound does? Sound waves are longitudinal. The vibration is back and forth along the direction the wave travels.
Like pushing a spring.
Exactly.
Yeah.
If light waves were like that, they should diffract easily. This is where Young and Fresnel came in, building on some suggestions from Young.
And he had the breakthrough.
He did. To explain polarization, this weird property discovered earlier, showing that light somehow had sides, it behaved differently depending on orientation. Fresnel realized the vibrations couldn't be longitudinal. They had to be transverse.
Meaning sideways.
Sideways. Vibrating perpendicular at right angles to the direction the light is traveling, like shaking a rope up and down. That immediately explained why light travels in straight lines and doesn't bend around corners easily, and it perfectly explained polarization.
And the wave theory just got stronger and stronger.
Culminating in this almost unbelievable moment in 1832. William Rowan Hamilton, purely from the mathematics of Fresnel's wave surface theory, predicted something totally bizarre.
What was that?
Conical refraction.
Yeah.
He predicted that if you sent a single specific ray of light into a certain type of crystal at just the right angle, it wouldn't just bend, it would spread out into an entire cone of light inside the crystal.
A cone from one ray. That sounds impossible.
It sounded crazy. No one had ever seen anything like it. But Humphrey Lloyd did the experiment very carefully and found it, exactly as Hamilton's math predicted.
Wow, so the math predicted reality before anyone had even imagined it.
That's the power of a good theory. It cemented the wave theory. The particle idea for light was, for the time being, defeated.
Okay, so while light waves were winning the day, there was this whole other area bubbling up electricity, but not just static sparks, moving electricity.
Dynamic electricity, yeah. And it famously kicks off with Luigi Galvani in the 1780s and a frog.
The frog leg experiment, everyone's heard of that one.
Right. The story goes, he was dissecting a frog near one of those static electricity generating machines. Someone drew a spark, and at the same moment, an assistant touched a nerve in the frog's leg with a metal scalpel, and the leg twitched violently.
Even though the frog was, well, not alive.
Not alive. So Galvani thought, aha, electricity isn't just from machines, it's in the animal. Animal electricity, a vital fluid.
Makes sense from what he saw, but that wasn't the whole story.
No. Along comes Alessandro Volta. He looked closely and said, wait a minute, it's not the frog, it's the metals. You had the brass hook holding the leg, the iron railing it touched, or the steel scalpel and maybe a tin plate. It was the contact between two different metals, with the frog's fluids acting as the electrolyte that caused the effect.
So Volta basically said, forget the frog, it's about the metals creating an electric tension, as he called it.
Exactly, a potential difference. And that led him directly to invent the first proper battery, the voltaic pile. Just stacking discs of different metals like zinc and copper, separated by cloth soaked in brine. No animals needed.
But the debate wasn't quite settled, was it? What was the ultimate source?
No, there was still argument. Humphrey Davy, for instance, did experiments showing the battery's power seemed directly related to how much the liquid could uh, chemically react with one of the metals, oxidate the zinc, he said.
So Davy leaned towards a chemical source.
He did. He argued the driving force was chemical affinity, which he suspected was itself fundamentally electrical in nature.
Yeah.
So was it contact? Was it chemistry? The lines were blurry.
But regardless of the source, they now had a continuous flow of electricity. They needed to measure it, quantify it.
Absolutely. And that's where George Simon Ohm comes into the picture. He wanted to make sense of the whole circuit.
How did he approach it?
He used an analogy, a really powerful one at the time. He compared the flow of electricity to the flow of heat, which was better understood mathematically.
Okay, heat flows from hot to cold.
Right. So Ohm proposed there was this electrical equivalent, call it electroscopic force. And the difference in this force between 2 points in a circuit is what drives the flow, the current.
And that electroscopic force is basically what we now call voltage, or potential difference.
That's exactly right. And he formulated his famous law. The current flowing is proportional to that force difference, and also proportional to the conductivity of the wire. Simple, elegant, and suddenly you could calculate things in electric circuits. It was revolutionary for making it quantitative.
All right, so we've got waves of light, we've got flowing electricity. Now we hit the mid-19th century, and Michael Faraday enters. He seems like a real game changer.
Oh, absolutely fundamental. Faraday thought differently. Before him, it was mostly about forces acting at a distance between objects. You know, magnets pulling iron, charges attracting or repelling.
Action at a distance. Spooky.
Right. Faraday wasn't comfortable with that. He started thinking about the space between things. He visualized these lines of magnetic force, essentially with iron filings around a magnet.
Those patterns, yeah.
For Faraday, those lines weren't just illustrations, they were physically real. They represented a state of tension or strain in the space, in the ether. And his big discovery, electromagnetic induction, came from this thinking. He found that you only induce an electric current in a wire if that wire cuts across these magnetic lines of force. It's the interaction with the field that matters. Moving parallel to the lines does nothing. Cutting the lines produces a definite voltage and electromotive force.
That's a massive shift. It's not the magnet acting on the wire from afar. It's the wire interacting with something real in the space right where the wire is.
Precisely. The field becomes the central concept. The lines of force aren't just a calculation tool. They are the physical mechanism. And this whole way of thinking, this focus on fields, laid the essential groundwork for James Clerk Maxwell.
Okay, Maxwell. Mid-1860s. This is where it all comes together, right? Electricity, magnetism, light. But the math gets heavy. Can you give us the key insight?
Maxwell's genius was taking Faraday's physical intuition about fields and turning it into rigorous mathematical equations. He described how electric and magnetic fields interact and change each other. But there was a gap in the existing laws. The equations didn't quite work consistently, especially in situations like charging a capacitor, where you have a gap between two plates and electricity builds up, but no charge actually flows across the gap.
Right, it's an insulator in between.
Exactly. Maxwell realized that even in that gap, the changing electric field itself had to be treated as a kind of current, what he called the displacement current. It was a current not of moving charges, but of the changing electrical strain in the ether, in the field itself.
That sounds abstract, but necessary.
Absolutely necessary to make the equations mathematically consistent and complete. It was the missing piece. And when he added that term and solved the full set of equations, well, the result was mind-blowing.
What did the equations predict?
They predicted that changes in electromagnetic fields should propagate outwards as waves, like ripples. And crucially, the equations predicted the speed of these waves.
And that speed was?
It was determined by fundamental constants of electricity and magnetism specifically, the ratio of the electromagnetic unit of charge to the electrostatic unit of charge, a number you could measure in the lab.
Okay, so a theoretical speed based purely on electrical measurements.
Yes, and people like Kirchhoff had already measured this ratio. The value was about 3.1 times 10 to the 10 centimeters per second.
Which is, wait a second, that's the speed of light.
Exactly. Within the errors of measurement at the time, the predicted speed of Maxwell's electromagnetic waves was identical to the known speed of light.
So light is an electromagnetic wave.
That was the unavoidable conclusion. Light, this thing they'd argued about for centuries. Particles, waves, faster in glass, slower in glass. It was an electromagnetic disturbance propagating through the field. Maxwell's theory didn't just describe light, it was light. And it even predicted other things, like light having pressure, which was confirmed decades later. It was a monumental unification.
Okay, Maxwell's theory is this incredible triumph. Unifies electricity, magnetism, light. Seems like physics should be almost done. But there was still that nagging problem of the ether, wasn't there?
Yeah, the ghost in the machine. If light is a wave, Maxwell's theory seemed to demand that it needs something to wave in. You still needed that medium, the ether.
So they didn't just ditch it.
Oh no, they doubled down. Physicists spent decades trying to build elaborate mechanical models of this ether. You had things like the vortex sponge theory or a labile ether that could somehow be both rigid enough for light waves but let planets pass through without resistance. It got very complicated, very contrived.
Trying to make a mechanical underpinning for Maxwell's mathematical fields.
Exactly. But then came the experimental blow. If this ether exists and the Earth is moving through it, we should be able to detect that motion, right? Like feeling wind when you ride a bike.
The Michelson-Morley experiment.
The famous Michelson-Morley experiment, designed precisely to measure the speed of the Earth relative to this stationary ether by comparing the speed of light beams traveling in different directions.
And they found
Nothing. Null result. No matter how the Earth moved, the speed of light always measured the same. There was no detectable ether wind.
which was a disaster for the ether theories.
A complete crisis. It meant either the ether was dragged along perfectly by the Earth, which contradicted other things, or it was somehow undetectable, or maybe it just wasn't there in the way they thought.
And this led to some pretty wild ideas to try and save the situation.
Extremely wild. To explain the null result while keeping the stationary ether, George Fitzgerald and independently Hendrik Lorentz came up with a radical suggestion.
What was it?
They proposed that maybe material objects, including the experimental apparatus itself, physically contract slightly in the direction they're moving through the ether.
Wait, things shrink when they move.
Exactly. Just enough to perfectly cancel out the expected time difference in the Michelson-Morley experiment. It sounds crazy, but it showed how desperate they were to hold on to the ether concept. They'd rather warp space than give it up.
While all this ether drama was happening, wasn't there another revolution brewing concerning matter itself?
Yes, totally in parallel. Experiments with electricity passing through gases at low-pressure cathode rays. J.J. Thomson's work in the 1890s measured the mass-to-charge ratio of these rays.
And he found
These cathode rays were made of particles far, far smaller and lighter than atoms. He called them corpuscles. We call them electrons. And crucially, they seem to be a fundamental component of all matter.
the electron arrives on the scene.
Right. And this tied back into Lorentz's work. He developed a comprehensive theory based on these electrons. He proposed that the ether itself is absolutely stationary, completely unaffected by moving matter.
So the ether doesn't move.
According to Lorentz, no. But matter contains these charged particles, these electrons, and it's the interaction of these moving electrons with the stationary ether that explains all the electromagnetic and optical phenomena, including how light behaves in moving bodies, fitting Fresnel's old laws perfectly. He even incorporated the Fitzgerald contraction into his theory as a physical effect on the forces holding electrons together.
So looking back, it's this incredible journey. We start with Descartes needing this physical, mechanical ether. Then Faraday and Maxwell make it more about fields, more abstract. And finally, Lorentz's theory explains everything beautifully by having electrons interact with a completely motionless ether, almost reducing the ether to just space with properties.
Pretty much. The quest for a mechanical model of the ether basically failed. What survived were Maxwell's equations describing the behavior of fields in space, and Lorentz's theory showing how electrons interacted with those fields. The focus shifted from the medium to the dynamics to the mathematical laws.
It's an amazing arc over nearly 3 centuries, from clockwork fluids to abstract fields and fundamental particles.
It really is. And it leaves you thinking, especially about that Fitzgerald-Lorentz contraction idea. Even if it arose for slightly wrong reasons back then, it plants this seed. If the very instruments we use to measure length and time can change depending on how they're moving.
Then what does absolute rest or absolute length even mean?
Exactly. If your ruler shrinks when it moves, how can you be sure about the dimensions of anything? It hints at this deeper, more relative view of space and time that was just around the corner. How much does reality itself depend on the observer?
A truly mind-bending thought to leave us with, something to definitely mull over. Join us next time for another deep dive.